Okay. It's my pleasure as President of the Global Environmental Change Focus Group to introduce this year's named Tyndall Lecture on the history of global warming. And it is going to be given by Bill Ruddiman, who constitutes both history and historian, as you will see. Just as John Tyndall showed 150, 160 years ago, through careful lab experimentation and calculation, the importance of the greenhouse effect in our atmosphere, so Bill has made a number of really significant advances in our understanding of our Earth and its climate, and the interaction between the solid Earth and its shape and behavior and the climate system. And so he is a singularly appropriate person to give our lecture today. I'm going to ask him to come up to this microphone, and I too will be presenting him with a certificate. So I guess he doesn't have to deal with the promotion tenure committee anymore, but he can keep it as a small memento of our appreciation for his being willing to make this lecture.
Thank you very much.
So, Bill.
You may notice I'm carrying crib sheets here. I've never given a lecture that I can remember in which I had notes, but this is a lecture I didn't want to miss any steps because there's a fair amount of intricacy, and it's a step-by-step kind of explanation. And so if my glasses will pull up these notes in this somewhat dim light, that you'll be treated to a talk that doesn't have steps missed. I thank the Global Change Focus Group, and particularly Steve Lloyd, who is the initial contact. Can you hear me in the back? Yes? As long as I speak into the microphone. Thank you for this invitation. It comes 10 years after I gave the Emiliani Lecture at AGU in 2003. That was actually, well, it was technically an invited lecture, but I nominated myself. It's departing from my usual modesty. I said, I've got a really interesting story and nobody knows about it, so I have to nominate myself. And so the nomination was accepted, and I gave the talk. And at the same time, this paper, same month, this paper was published in climate change. Now, this lecture, I think, has the title, The History of Global Climate Change. The history of this lecture is only going to be about the last 10 years of doing science. The history that it covers in terms of evidence is going to go back thousands of years. And that paper was a challenge that the anthropogenic era started thousands of years ago, not in and around the 1800 to 1850. And I'm going to assume you know everything that you need to know about the industrial part of the anthropogenic era. So the focus here is going to be on the previous part of the era. Now, this hypothesis has generated a lot of argument, and it hasn't been universally well received. I was really curious what the response was going to be. I've only shown this slide once before, and I showed it at Lamont. And I got a huge laugh there, so this is clearly a different audience, and I'm not sure what to make of that. Now, Dr. Broker's obviously a great scientist, but he part of the history of this debate are statements like these, which have had an impact on the degree of acceptance. Steve Schneider called science a contact sport, and that's very much evident here. The actual main history of the 10 years of the debate has been one in which science has been working the way science usually works, which is that there have been papers favoring this view, and there have been papers opposed to or my view, and papers opposed to it. And so there was good evidence from the start on both sides. I had some good evidence for what I said. Other people had good evidence against my hypothesis. So that the process of science has been working itself out. In any case, and there have been some 50-some papers published testing this hypothesis in 10 years. And here I am giving this debate. So I guess from my point of view is I'm still walking, and that's not all bad. This talk is going to it's going to have a certain rhythm to it. I'm going to show slides that you'll recognize as being in black and white, which are from that 2003 paper. So these are slides that show my, and the word "my" is going to creep in here because, well, it was my hypothesis. So these slides are going to show what I said or what I projected back 10 years ago, and then the color slides that are in between these will show the new evidence that's developed as people have come up with new ways to test the hypothesis. This slide shows a prediction about what should have happened to the methane trend in the last 10,000 years. And I predicted that the methane trend should have followed the Northern Hemisphere insolation trend, because Northern Hemisphere insolation it was common knowledge by that point that Northern Hemisphere insolation was determining the phasing of the methane response. And instead it reversed and went up 5,000 years ago. And that looked to me like a wrong way trend. And I said so and said the trend should have gone down. And one reason I said that was there were 3 interglacials that had been previous interglacials that had been drilled at Vostok. And they the methane trends all went down, but the Holocene went up. Well, now we're in a point where Dome C has been drilled. We're all the way back to stage 19, and that's all but one of the so-called 100,000-year interglaciations or glacial cycles. And here's the situation. The Holocene trend is shown with the red dots. There's that early Holocene peak around 10,000 years ago. There's a rapid downward trend till 5,000 years ago, and the trend goes up. That's pretty much what I showed you in the data from the last slide, which was work by Blunier. Now, the data shown in blue is an averaging of previous interglacials, and they're all aligned on the first precessional insolation minimum within each interglacial, and those have been, and they're dated by the EDC3 timescale of Perinen et al. And the first precessional minimum is assigned based on the astronomically dated orbital variations. So the dark blue circles show the average variations in 1,000-year bins for those 7 prior interglaciations, and the red, as I said, shows the Holocene. You can see that, and the light blue shading is the standard deviation. You can see that the Holocene is different. the average of the previous interglacials all went down in the last 5,000, or the period comparable to the last 5,000 years, and it went down in every one of those interglacials. So only the Holocene goes up. To me, this is powerful evidence that prediction that methane should have gone down is a correct one, and that the rise since 5,000 years is anomalous. I call this top-down evidence, and I'll come back to that phrasing shortly. Now, there's new bottom-up evidence that's been emerging the last 3 or 4 years. This is work by Dorian Fuller, who mapped the spread of wet rice agriculture out of China and across Asia from 5,000 years ago up until 1,000 years ago, as shown by the scale at the bottom left, and red is the data points. And you can see there's a 5,000-year interval. Well, the rice agriculture starts just before 5,000 years ago, and it spreads throughout that 5,000 years. Now, Dorian, who's an archaeobotanist at University College London, took that data and produced the figure at the top, which shows the area in rice agriculture. And he did that by taking the date of the first arrival of rice agriculture in each of those mapped regions, and then by assuming that the infilling of more dense rice agriculture followed the square root of the population trend. And he came up with a rising exponential curve, which between 5,000 years ago and 1,000 years ago rose enough to put CH4 emissions in the atmosphere to sustain 70 parts per billion. The actual rise is 100 parts per billion. So rice agriculture alone is explaining a serious part of the observed rise if his pioneering work is correct. And he's just been funded with 2 huge grants to pursue this for the next 3 or 4 years. But remember, the anomaly is not just the rise, but it's the fact that the methane concentration didn't go down, so the failure to decrease is a part of the story too, which means there's more to explain than just the 30 parts per billion difference between these two plots. And Dorian also mapped in Asia and in Africa, which isn't shown here, the first appearance of livestock. This is a radiocarbon dated archaeological remains. And you see that between 7,000 and 5,000 years ago, there's livestock in a few arid regions and not very many data points, but between 5,000 and 3,000 years ago, livestock get into pretty much all of India. They get into China. They're down in parts of Southeast Asia. And 3,000 to 1,000, there's a little bit more infilling. So there's reason to think that livestock are powerful emitters of methane. So there's reason to think that that's going to contribute another big chunk to the observed methane concentration. In fact, I think it's reasonable to think that this bottom-up evidence of livestock and methane coming from archaeology may converge on the size of the anomaly that I claimed, which is about 250, 300 parts per billion. Looks like it's going to explain a good chunk of that. Now, there's a similar story with CO2. This is the next figure from that paper. This is Vostok data again, and you see the CO2 trends in the Holocene trending upwards, or first down and then up, and I projected a CO2 decrease. And so I said everything before 7,000 or 8,000 years ago on that time scale was natural, and everything after 7,000 years ago is anthropogenic because it's going the wrong way. Here's another similar plot of stacked and binned CO2 data in blue, the average and the standard deviation, and the CO2 trend in the Holocene. And here there's a quite remarkable, there's a lot of scatter because the recent interglacials have generally higher CO2 levels at the peak, and before 400,000 years they have lower values, but it's pretty clear that the Holocene trend looks pretty natural till about 7,000 years ago, and then it goes up. Not as an exponential though, which is interesting, and we'll come back to that. Now during this time, this 7,000 year period, agriculture is spreading across, got a nervous finger here, is spreading across the world's continents. You can see the numbers in white are in thousands of years, the date that the spread began from source regions. The Fertile Crescent, 9,000 years ago. Northern China, 9,000 years ago. Southern China, 5,000 years ago. Sahelian and North Tropical Africa, 5,000. Mexico, 4,000. And Peru, 4,000. So all through that 7,000 year interval, more and more forest is being cleared in more and more areas. And to just give you a figure for the texture of the data, here's Europe. Prior to about 8,000 years ago, the Fertile Crescent source of domesticated livestock and crops, wheat and barley and peas and lentils, is constrained to Southwest Asia, starts creeping into Greece, but around 8,000 to 6,000 years ago, explodes across Africa. This is C14 dated archeological sites, and there's a further proliferation by 5,500 years ago. Now, just for perspective, this is all Neolithic. This is all Stone Age. We're still a bit short of the Bronze Age. So there's people farming all over Europe, pretty much everywhere where people farm today. And they start to do that between about 8,000 and 5,000 years ago. Well, that's just when the CO2 curve goes anomalous. It starts upward. In China, we don't have quite that kind of data, but there's a paper by Li et al. That was published 2 or 3 years ago, and they showed for an interval 8,000 to 7,000 years ago and an interval 5,000 to 4,000 years ago, they showed the increase in just total number of dated archeological sites. It's probably true that not every site was dated, but in China there are cultures which last for a few hundred years. The cultures are dated in one place, and then that can be used by itself to restrain the ages of some sites that haven't been dated. Anyway, between 8,000 and 7,000 years ago and 5,000 and 4,000 years ago, there's a 30-fold increase in the density of archeological sites. If that's a measure of population, and it should be at least some measure of population, that's a doubling time of 600 or 700 years, which is extremely rapid. So, and all those people are farmers, so they're all clearing forests and they're all emitting CO2 to the atmosphere. Now, I made a crude estimate in this cartoon of rates of delivery of billions of tons of carbons per year into the atmosphere in pre-industrial time compared to industrial time. And you'll notice that the pre-industrial time, there's a very slow increase and the rates are quite low, and then there's this well-known explosion in the industrial era. But if you integrate under those curves, I predicted that there would have been 300 billion tons of carbon emission before 1850, which is what most people are using for the beginning of the industrial greenhouse era, and only 150 after, during the industrial era, so about a 2-to-1 ratio. Now, and so I'm going to deal with that subject and look into it in more detail. I should have said that was all deforestation carbon, no fossil fuel carbon. Now, first, the most common criticism of my hypothesis has been pretty much summarized by this figure. CO2 after 7,000 years ago follows that trend, and it's It's kind of a fast early rise and then a leveling out and a slow later rise. Population, according to one of the geometric models used, follows the trend at the bottom. And you got a problem here because the cause that I claim, which is the population increase, comes after the effect, which is the CO2 rise. And that looks like a fatal flaw for the hypothesis. However, that's true only if you assume that each person was responsible for clearing the same amount of land all the way through those 7,000 years, and that's just not the case. The records of what you would want as real control of what clearance has been, the reliable records, as you can see, are basically 1950, 1960 or later. That's the Food and Agriculture Organization. And so even to reconstruct clearance in the most of the industrial era, you have to do an extrapolation backwards from 1960 or 1950. And to make things worse, there are areas like Europe where the whole interval since 1800 has been reforesting, not deforesting. There are enough surveys, not annual, but there are enough surveys to show that regions like France, Sweden, and the UK are reforesting. So how do you hindcast deforestation if your database, if your control case is reforestation? It's a difficult problem. There's another view out there among the archaeologists, and that is that it's very different from the assumption that's often made of one person, 1 hectare of clearance of woods for agriculture. And this comes from Esther Boserup, who is an economist who was working actively in 1960s to 80s. And this cartoon summarizes one aspect of her hypothesis. You start with a forest of mature trees, as shown on the left. You clear them, probably using a stone axe, and then just burning dead debris in a dry season. You stick sticks in the ground to plant your seeds. You use the ground for 3 or 4 years till it's used, the fertility's gone, and then you move on. You move to another plot. And so that ground you use each year might be just a hectare or 2, but you're leaving a footprint shown by those black arrows behind you. So the per person footprint is much higher than 1 or 2 hectares because of this footprint that you're leaving behind you. And there's historical data on land use that supports this. That Boserup, in fact, makes the case that she's basically right. Up top, I'm showing cultivated hectares per acre in China based on a data set assembled by John Buck in Nanjing in 1937 and re-examined in a book by Zhao, University of Chicago Press, 1986. And you see a 4-fold decrease in cultivated acres. That's only a portion of land use between 2,000 years ago and the just immediate pre-industrial era, from 0.6 or 7 down to 0.17. So people used a lot more land 2,000 years ago, partly because of that effect I just showed you. They're using less, much less in recent centuries. Same thing is true for Europe. This is data assembled by Jed Kaplan, but earlier assembled by a number of Europeans. This happens to be hectares cleared, hectares of forest cleared. So it's the cultivated land, the pasture, the wood harvest lots, and all the rest of it. And that trend, so those are much larger units, people using much more land per capita. But the units are different, but the trend is the same. It's a factor of 4 decrease in land use. Europe and China are the only places where we have records like that, but they're both telling you the same story. What they're telling you is it's not one person, 1 hectare. The consequences of this difference in interpretation are huge. If you assume that every person cleared just 1 hectare of land throughout the 7,000 years, you end up with a projection for Europe where Europe is still about 50 to 60% forested in 1800. And there's a problem with that because I just showed you that Europe is reforesting since 1800. So you're in a logical dead end. You can't have Europe 60% forested in 1800 and then reforesting. That means Europe never got deforested. Well, it did and is predominantly at levels like 80, 85%. On the other hand, if you use that historical land use data, which is what Jed Kaplan did, you come up with a Europe that's 70, 80% deforested by 1800, even up to 90% deforested. That's consistent with a Europe that's going to reforest for the next 200 years. So, to summarize this portion of the argument, I made this projection that here I showed 320, other cartoons showed 300. 300 gigatons of carbon were released in pre-industrial time. I did that by assuming that most of Europe, most of China, most of India, and parts of other regions were deforested by 1800. And then I didn't explicitly say what the industrial era deforestation was, but I was assuming the 150, 160 number is correct. Now there's several papers that are either directly based on the hide reconstructions, which are used on the right. That's the 1 person, 1 hectare assumption of land clearance. And so Strassman et al., Stocker et al. Directly used hide. Julia Pongratz did her own analysis, but it amounted to pretty close to 1 person, 1 hectare. And what they got was pre-industrial deforestation in the 50 to 70 range. Now that's 4 or 5 parts, 4 or 5 ppm. It's not a very large effect. And then the same, more or less the same industrial era deforestation. Jed Kaplan comes along. He's using the historical data, which I argue is the only data that's reliable for trying to do this. He gets 343 in pre-industrial time and 108 in industrial time. So 3 to 3.5 times as much clearance in pre-industrial times as since industrial era times. So that crude guess that I made back in 2003 is looking pretty good. As with Dorian Fuller and the rice agriculture and the livestock data, same thing with Jed. This is a first pioneering attempt at what I think are valid estimates of pre-industrial land use, and there'll be more. There'll be lots of refinements coming, but it's a big number. Now, so that takes care of another challenge to the early anthropogenic hypothesis. There was a lot of land clearance before 1850. Now, another impressive challenge to the hypothesis came from the Barron Group, who analyzed the Del 13 CO2 trend over the last 7,000 years. And they found a very slight negative trend, and it's indicative of very slight net negative release of terrestrial carbon over 7,000 years. They then broke that down with a mass balance analysis into 3 different groups of factors. One was a small 40 gigaton peat burial. That's you're burying carbon, that's not releasing, it's the opposite, so it goes in the other direction. Another was the natural release of carbon as monsoons weakened and things dried out. And then they took the Strassman et al. Estimate of carbon emissions and their estimate was 3.5 parts per million CO2. So that's a killer if it's correct for my hypothesis. However, there are estimates out there that suggest that something like 300 gigatons, billion tons, is much more accurate than 40. There was early work by Evel Gorham, and then recently a major compilation by Zaicheng Yu, and both of those came up with something like 300 billion tons of peat burial. Now, if you keep the Del C13 trend the same, which it is, it's the same data, and if you keep the monsoon input the same, you have to come up with 300 gigatons of emissions somewhere, and that leaves anthropogenic. So 300 billion tons of release of anthropogenic emissions is consistent if peat burial is that large. Now, I just stumbled last week on a paper in Climate of the Past, and 2 members of the Burn group are on this paper, and they show 300 billion tons plus or minus of peat burial. So my reading of that is the Burn group has in effect abandoned the upper mass balance, which was used to argue against my hypothesis. They're accepting the 300 billion major burial, which requires major anthropogenic emissions. So here's where I think the CO2 argument is, sources of carbon to explain my hypothesized 40 parts per million anomaly, the CO2 trend going up instead of going down. Deforestation would give you 23 to 24 out of the 40. There's a little bit comes out of coal burning in China, which has been going on for 2,000 years, and a little more from peat burning in Northern Europe, which has been going on a few centuries. You might get 1 or 2 parts per million. If there are emissions plus the methane, if there are emissions that large, it not only warms the atmosphere, it either warms the ocean or it keeps the ocean from getting cold, if that's the ocean's natural trend. And if you try, we've, with John Kutzbach, we've run models that estimate the CO2 solubility, or the ocean cooling, and we come up with a 7 to 8 parts per million CO2 solubility feedback. So the ocean's staying warmer or getting warmer than it should have. And if it's doing that, it's giving off carbon because a warm ocean holds less carbon. So now you're up to 33 parts per million. You're beginning to converge on the anomaly that I suggested. And the Southern Ocean is still another possibility. We don't have an estimate on that, but models are just getting to the point where you all probably know the Southern Ocean's a center of action for CO2. So it's a good chance that that we'll get some more feedback out of the Southern Ocean. Now there's still one problem, one discrepancy in the story that I tell, and that is that there's that CO2 trend again, there's that late rising population trend. I showed you that Jed Kaplan got earlier carbon emissions because of higher per person land use. And roughly speaking, that boosts the carbon emissions curve up from the population, the geometric population curve, by about the amount shown in green. You're moving towards the CO2 curve, but you're not there. Well, here's something that fascinates me. There are other models for population growth. The geometric model has that fast rising, late rising exponential, and it's predicated on the assumption that all the environmental conditions that controlled population growth were absolutely constant for 7,000 years. Whether there's 100 people in the world or 1,000 or a million, it's the same fractional growth rate. But there are models out there that are called logistic models. These are used widely by ecologists. And these show, they have the form shown there, kind of a sigmoidal shape, with a rapid rise and then a slowing. And the reason the ecologists use them is that the resources start to give out. Growth is fast when resources are abundant, and slow when resources start to give out. And there's other factors that could enter in, like pandemics and other things as people start crowding up. There's some data to support, there's some model data to support this. Karsten Lehman's been impressive in this kind of work. So those red patterns up there are 3 different models of his that are more of a logistic shape than a geometric shape. The top model, the one in 2003, actually plots right on top of the CO2 curve. So that rises populations rise so early that you can explain the CO2 curve just by that. His more recent work has backed that off a little bit, but it's still way above the geometric curve. So I think there's every prospect that a reasonable logistic curve plus the boost you get out of the Kaplan per capita emissions is going to give you those early CO2 emissions. It's kind of amazing. We're still arguing about something as basic as when was the rise in our species population in the Holocene, but we really don't know. But European and Chinese records go back 2,000 years. Most records don't go back more than 500 or 600 years. There's DNA evidence coming out. This is work by Guignot et al. In PNAS, and that shows the growth rate of the female population, mitochondrial DNA, the variability of mitochondrial DNA grows with the size of the population. And for Europe, the fastest growth rates, and note this is a log scale, not directly comparable, fastest growth rates are 6,500, 6,000 years ago. The absolute growth is fast, larger later, but the fastest growth rate is early, and that again is moving towards these logistic models. Okay, so I think I've got enough. Yeah, I've got enough time. 2 more aspects of the hypothesis. I thought I detected a link or a correlation between pandemics and CO2 trends. And this was pretty brave. It turned out that the CO2 trend that I was showing, I think I must have just smoothed it for a cartoon, was from Taylor Dome, and that turned out to be misdated at that point. So the time scale on that was wrong. And I was only showing pandemics. I didn't know that much about civil strife, which is also a factor. Well, here's the modern situation. Now we got a lot of data, the ice core data, Law Dome, and some other areas, but this is all Law Dome. Lots of data points, nice coherent trends, and plotted in the middle is major depopulation episodes. And the orange or tan colors show you times when the CO2 level was significantly going down, and at the bottom you pick up times when the methane level was going down. And the figure links these to depopulation episodes across the globe. So 200 to 600 AD, you're getting a serious population decrease both in China and in Europe. In Europe, it's the first bubonic plague. China, it's civil strife. 1200 to 1400, you get Genghis Khan going into China and ripping up the irrigation infrastructure, which affects methane. You get the Black Plague, which is very brief. And so you're getting 10 to 15% of the population dying in these episodes. And then the the really big one is the Americas. You get a 50 million estimated early American deaths. The population goes from 55 or 60 down to about 7 million just because of every disease known to humanity. Those are all pretty good correlations. And there's a movement in people in the ice core community, the ice core geochemists, particularly with the methane curve, they're getting behind the idea that the methane abundance shows a better correlation to population drops than it does to regional precipitation or regional temperature. I think I'll skip 2 of them and go to the last claim in the hypothesis, which is that, it's not the one, that a claim that there's an observed climate at the top. There's a climate that would have happened, I said, if greenhouse gases hadn't intervened, and you would have gone through a glaciation threshold by now. I said this for some reason I picked 5,000 years ago, which is way too early, but the point stands that it would have gotten cold enough by now if early anthropogenic greenhouse gases weren't emitted the way they were. And there's a relationship that favors this claim. This is a figure from a recent paper by John Kutzbach, Steve Vavris, the Wisconsin group I've been working with for 9 years. Shows you something you already know, but as you get to lower CO2 values, especially below 300, the amount of cooling you get per unit of CO2 decrease is larger. It steepens. And so you get a very large pre-industrial cooling if you take out the early anthropogenic greenhouse gases. In fact, you get a slightly larger cooling than you do during the industrial era. There's other factors that play into that. I guess I should name those factors. You know that industrial aerosols have canceled part of the industrial era cooling, and the slow response of the ocean has canceled part of the cooling. But at any rate, this relationship is in favor of making modest-looking greenhouse gas increases pre-industrial have very substantial temperature effects. And we've estimated from a range of model runs that the difference between an 1850 world without any prior early anthropogenic greenhouse gases and one with the gases, which is the one that happened, is 1.1 degrees centigrade. There's a range of a couple of tenths of degrees centigrade in different experiments. Now recently, Marcotte et al. Just published the observed trend of a 0.7 degree decrease in temperature. We're saying there would have been another 1.1. And so if this is right, the true anthropogenic net effect, all factors considered, is more than double the industrial era warming. Because the industrial era warming not shown here is about 0.85 by now. We're saying the pre-industrial warming that canceled a major cooling was 1.1. Now, that sounds ridiculous at first hearing. 1.8 degrees centigrade, that's 40% of the glacial maximum cooling relative to the Holocene. But look at the forcing. Solar insolation right now is somewhere around 50% of the range of values it's been at in the last 300,000 years. It can be much higher than it is now. It can be considerably lower. We're at about the 50% point towards the lowest insolation, therefore the coldest climate. CO2, which is the major greenhouse gas forcing, I'll ignore methane, is also in about the 50% range. If our projections for the no anthropogenic world are correct, we would be at about 2 to 45 parts per million, which is about halfway between the glacial and the interglacial. So the insolation is giving you enough forcing, and if the hypothesis is correct, the greenhouse gases would give you enough of the rest of it to say, yes, we would be 40 to 45% of the way to a glacial climate now. And so we have run, this is Steve Vavris, John Kutzbach, the Wisconsin group, run several experiments with a world stripped of the greenhouse gases down to levels that I claim they would be at, and for which I've shown you pretty good evidence today. And the areas in white, ignore Greenland, but the areas in white would have permanent snow cover, 12-month snow cover. These are GCM models. They can't do long simulations. But basically what they're saying is those areas would either have growing glaciers or at least ice caps that never melt in the summer. So it's parts of Siberia, it's the northern Rockies, it's the usual area of glacial inception in northeast Canada, an area totaling about 30% larger than the Greenland ice sheet would have small ice sheets growing. So that supports that claim that was made. So my reading is that all the claims of the early anthropogenic hypothesis are at least alive, and some of them are thriving. And the arguments, the way the arguments are going at a larger level is there's this top-down evidence that show that the Holocene gas trends are not the trends in previous interglacials. Somebody probably want to ask me about stage 11, and I've left time for a lot of time for questions. So the top-down comparison to previous interglacials gives you a target number for how large the early anthropogenic effect could be. And now what's happening the last 3 or 4 years, and this I think is going to change the game for the next several years, is that work like Dorian Fuller's work on the rice irrigation and future work on livestock and Jed Kaplan's work on land use are giving you bottom-up numbers based on archeology, land use history. And if those two numbers, if those bottom-up numbers start to converge on the top-down numbers, it's going to be very hard to argue against the early anthropogenic hypothesis. So I think there's probably 10 minutes or so for questions.
Thanks.
I forgot to say that there's a little brazen self-advertising here. This book came out in October. It's a full-color textbook, and it'll be out in electronic version I think in February. One's $55, the other's $30, so it's not textbook price quite.
Thanks so much, Bill. Now we start the question session. Make sure speak to microphone when you have questions. Thank you.
So Wally had some pretty strong words, and I'm wondering what his primary objections were in 2009 and if any of those have been satisfied.
His primary objections, we were actually in pretty good touch for a number of years there until about that phase. And his reaction, he was struck by the Del 13 CO2 argument, which looked very powerful. And he was struck by the mismatch between the early rise of the CO2 curve and the late rise of the assumed geometric population curve. And so those, as usual, he's using good reasoning. But he really didn't like my ideas. And when I stayed stubborn, he got mad. So that's when we got into that phase. But I still very much respect the man.
So actually two quick questions. The first is, this work is weirdly interdisciplinary. Could you talk a little bit about how you got in contact with some of these other authors? I mean, your papers have reference citations spread over a amazing variety of different journals. So that's the first question. Second question is, in effect, does the data on gyrations from wars and plagues mean that the particularly multi-decadal variability in temperatures, a lot more of that was human and not part of the natural variation?
Yeah, I'll take the second one first. I focus mostly on the Little Ice Age because it's a big CO2 anomaly. It's 10 parts per million for a couple of decades, and then it stays 7 or 6 parts per million down. There's not a volcanic eruption right on that time, and the Maunder minimum comes decades later, so there's no obvious forcing for it. So that episode, I would claim, is 70% CO2. 70% of the CO2 fall is reforestation after people died. I think there's a similar effect, smaller effect on some of those other episodes, but I think the basic trend behind the last 2,000 years is a slow, orbitally driven decrease in temperature, big volcanic spikes on top of it, not much solar, and a greenhouse curve that is influenced by humans. So I would say it's a factor, but it's not the dominant factor. As for finding out, finding people, I guess it's kind of a mixed picture. I sent a paper working with some Chinese colleagues trying to map the spread of rice in China because I thought that's got to help put some numbers on it. And Dorian was a reviewer for quaternary science reviews, and he was anonymous at first, but I said, is that you? Basically because he cited himself and the things I should read. And he's a great guy, but he's a marvelous archaeobotanist, and so just the fact that he reviewed a paper where I was taking a blind stab at something that I wasn't qualified to do, and then he went and did it right. I mean, anything he does, you can take to the bank. Jed Kaplan just independently somehow got convinced that, I haven't asked him that question. He got convinced that the limited amount of historical data in Europe was useful, that people were using much more land than people thought. I had cited in that 2000 paper the Domesday Book, which says that England was 85% deforested in 1086. Now, if you have a linear relationship between population and clearance, there's 60 million people in the area I'm talking about now, and there was probably 3 or 1 or 2 million back then. So Europe ought to have been about 3% deforested, and it was 85%. And I thought, and that there's been some very good work done to check that number is a good estimate. So I had hinted at it, but then I just wasn't getting any major support from anybody else. And then Jed picked it up and did that work, which is, I think that's pioneering, that reconstruction that he's done of lots of early land clearance.
I have two questions that are related to each other that both have to do with tillage of soil. When you refer to deforestation, I presume you're referring mostly to loss of carbon from above ground forest biomass. But of course, when soil is tilled, we lose a lot of carbon as well, and it takes a long time for it to regain. Often it doesn't get back to the same level within a century or so. So I'm wondering if some of the shape of the curve that you were showing with CO2 could be due to larger losses with initial tillage, and then with return and slash and burn, smaller losses later. And related to that is that when it's tilled, nitrogen is mobilized, and we also see an increase, a very slow, gradual increase of nitrous oxide over the Holocene as well. Have you compared your trends of CO2 and methane with nitrous oxide by any chance?
I haven't looked at nitrous oxide, partly because, well, I was going to try and compare them to previous interglacials and see if the nitrous oxide trend went the wrong way. But as I recall, I looked at it, and the previous interglacials, the trends were not, they weren't well enough defined to make the comparison. As for soil carbon, I followed, in my initial guesses, I followed things like basically Ski Houghton's work, where if you clear forest, you get a lot of above ground carbon going into the atmosphere, but I think about a third of the total comes out of the upper layer, the active layer of the soil. So I just leaned on the experts.
Would you say there are any policy implications of your work as opposed to the previous model that was talked about, where the primary anthropogenic influences were a couple hundred years old? How would this change any recommendations for what we should or shouldn't do in the future?
I'm a mainstream person on climate science and general global warming, so I'm right with the mainstream on what's happened the last 100 years and projections for the future. So the way I look at what I'm proposing is the last 150 years are about the same, or pretty much the same as we all think it is. It's just that it comes up from a different baseline. There's an earlier baseline that's much lower, so that the total greenhouse gas effect is larger, the total temperature effect is larger. Like I said, more than doubling maybe our temperature effect on the planet. I have thought recently there's one effect that could enter into the policy area, and that is, people have done calculations on who's responsible for how much carbon in the atmosphere over the industrial era, and the U.S. comes off very badly in that calculation, deservedly so. But if you go back, and if there's 300 gigatons of clearance before 1850, that's going to bump up the fraction from China and Europe and India and a lot of other places. And ironically, the early Americans did a lot of forest clearance too before they were nailed by the pandemic, or the pandemic.
So if I could just follow up one more thing, then why was the criticism of one of the people at the beginning that it would give a fuel to the climate change deniers? I don't follow.
I have to sit down and scratch my head to remember how I can understand that. It just doesn't seem, at first blush, it doesn't seem logical to me. I guess it's something like, well, see, the industrial era is not as bad as we thought. We've been doing this forever, and to me, the central fact is we've done twice as much warming as we used to think. It's more fuel for the deniers to deny, as far as I'm concerned.
I read your seminal article in the Scientific American several years ago and was absolutely bowled over by the implication, which is that mankind has been doing the geoengineering of our planet for the last 8,000 years inadvertently to keep the climate relatively stable, and that's allowed civilization to develop with a little hiccup in the little ice ages when productivity went down. We almost lost it, but we recovered, and then we had some very stable climate during the British Empire, which was crucial for that to be a success. And now we have a great civilization, but we've done some very bad geoengineering by putting a lot of CO2. Isn't it time that we now did a bit of kind of reverse geoengineering to try and get the planet back into a good shape for our future?
I'd pretty much stay away from those kinds of what Gavin called advocacy. I would just be happy to get the Republicans to acknowledge the science. That's my advocacy.